These two loops add up the same numbers. Same array, same 16 million additions, same answer. The only difference is which loop is on the outside. Two lines swapped. So they should take the same time. They do not. The first finishes in 7/10,000ths of a second. The second takes 48 thousandths. "68 times slower, on my machine, from swapping two lines. Yours will give a different number, but not a small one." Same instructions, same data, same machine. By the end of this video, you will know every part of that gap. The processor is not the bottleneck here. It is waiting. To understand the wait, you have to know how memory actually answers a question. RAM is not a long list of boxes. It is a grid of tiny capacitors, each holding a charge. And a capacitor leaks, so every row gets read and rewritten thousands of times a second, just to stop your data evaporating. Now ask for 1 byte and watch what actually happens. The chip cannot fetch one cell. It activates an entire row and copies all of it into a bank of sense amplifiers. Then it hands you your 1 byte. The rest of the row is still sitting there, already paid for. The expensive part was opening the row. Reading the byte was almost free. Which means the next byte, from that same open row, costs almost nothing. So memory does not have one speed, it has two. Reaching a new place is slow, continuing is fast. Everything else in this video is built on that one asymmetry. Loop A takes that bet. Loop B fights it. A trip to main memory costs about 70 nanoseconds. That number is useless. Nobody has any feel for a nanosecond. So stretch the entire scale until one of them becomes a second. If reaching the L1 cache took 1 second, then L2 would take about 4, and L3 about 14. Main memory would take 1:10. That is the jump that matters. Your solid-state drive would answer in 28 hours. A spinning disk, 4 months. And a round trip from London to New York would take 5 years. The ratios are real. Only the units are stretched. That gap has a name, the memory wall. Processors got about 1,000 times faster over 3 decades. Memory latency improved by roughly 10. The two lines came apart and never came back. So caches exist to hide that weight. And the first thing to know about them is what they actually move. Ask for one integer. 4 bytes, you will not get 4 bytes. You get a whole cache line. Memory does not deal in bytes, it deals in lines, and there is no way to ask for less. How big is a line? On most desktops and servers, 64 bytes. But on the Apple Silicon machine I am recording this on, it is 128. That is not a guess. You can ask your own machine, Sysctl hardware cache line size. On Linux, getconf level 1D cache line size. And here is the number that explains this entire video. A 128 bytes per line divided by 4 bytes per integer is 32 integers. Every single time. Use all 32, and the cost is split 32 ways. Use one and move on, and you paid the whole cost for one. Which brings us to the loops. A two-dimensional array is a convenient lie. There are no rows and columns in memory, only addresses. Row 0, then row 1, then row 2, laid end to end in one straight line. So the next column and the next row are wildly different distances. Watch both loops walk the same memory. Loop B moves along the rows, which is the order the data is actually stored in. Loop B moves down the columns, jumping the whole width of the array on every single step. Same cells, same count, the worst possible order. So what did Loop B pay for? It needed 4 bytes and it fetched 128. It used one integer out of 32 and threw the other 31 away. And by the time it comes back for a neighbor it discarded, it has walked the entire 67 megabyte array, so that line is long gone. It fetches the same line 32 separate times. There is a second trick going on, and it is a gamble. The hardware watches your addresses. If you have read 3 in a row, it fetches the next few before you ask for them. When it guesses right, the 70 nanosecond wait simply never happens. That is why Loop almost never waited. Now break its heart. A stride of 1 is predicted perfectly. Even a fixed jump is fine, because the prefetcher learns the stride and follows it. But pointer chasing is unpredictable by construction. A linked list is the worst case there is. Every address depends on the one before it, so the prefetcher cannot run ahead. One caveat, so this does not sound like magic. Prefetching does not make memory faster. It overlaps the wait with work you were doing anyway. The 70 nanoseconds still happen, and a prefetcher that guesses wrong evicts lines somebody did want. So what does this mean for code you actually write? Suppose you have 1,000,000 points and you only want the x values. Store them as one array of structs, and x, y, and z sit interleaved. 2/3 of every line you fetch is data you did not want. Split them into 3 separate arrays, and every byte you fetch is a byte you use. This is not a micro-optimization. Whole architectures exist because of it. Analytics databases store columns rather than rows, so a query that reads one column reads nothing else. Game engines split entities into parallel arrays to keep the physics loop sequential. And now the part that keeps you honest. None of this matters until your data is bigger than cache. A 1,000-element array fits in L1 and lives there. Loop it in any order you like, and you will not measure a difference, because there is none. Our demo used 67 megabytes on purpose. So where did the 68 times actually go? Not one cause. 3 multiplying together. Every fetched line was 97% wasted. The prefetcher could not help a strided walk, and the sequential loop vectorized, while the strided one could not. Every one of those is about the order you touch memory in, not the arithmetic you asked for. So go and get your own number. Any language will do. The array just has to be far bigger than your cache. That is the part people get wrong. Next time, the same core running thousands of things at once, and the operating system that keeps them apart.